那个唐老师，要不然你开始啊，还是你做这样？
我开始。
好好好好好。
Okay, dear friend, good afternoon. So let's start our first session. In this session, we are very glad to invite Dr. Zhang Yi to give us a presentation. Dr. Zhang is graduated from the University of New South Wales with a master's degree in photovoltaic and renewable energy engineering and a doctor's degree in engineering. And now he is a lecturer from the College of Energy and Electrical Engineering of Ohio University. And today he will give us a presentation entitled PV in Buildings, Low Energy Buildings and Photovoltaic. So let's welcome.
Okay.
Dr. Zhang, please.
Thank you, Dr. Tang. I'm very glad to give us a presentation about the PV in buildings. Actually, the PV is abbreviation for the photovoltaic effect. So, what is the photovoltaic effect? Actually, the photovoltaic effect is to convert the solar energy into electrical energy directly without any other energy conformation. So the BIPV is actually the full name of the BIPV is building integrated photovoltaic, which means sometimes we use the PV panel installed on the buildings, and sometimes we will integrate the PV modules into the building as a whole energy power building, which means such kind of building can power by themselves through the photovoltaic module of solar cells. So today we will go through two sections. The first one, we will talk about the BIPV typologies and the integrations. And the second section, we will briefly introduce the basic characteristic of the photovoltaic solar cells, which is fundamental for the photovoltaic power generation. And so we will come to the first section. So we will look at the learning outcomes of this section. Firstly, we will be familiar with the BIPV typology and the potential for PV integration in buildings. In this section, we need to know the definition of what is the BIPV typology and the potential for its building. And the second point is we need to understand the integration issues for different BIPV technologies. And then according to this, we will select and locate the PV system components for buildings with consideration of first one is the power output, we are also including the system sizing. And the second is the solar irradiation, shading, and mismatch problem about the PV systems. The third one is we will talk about the temperature and the ventilation effects on the solar power output effect. And we will also discuss about the effects on buildings and aesthetics. And we also will talk about the town planning consideration and the installation and the maintenance of the BIPV systems. Finally, we will go through the size grid connected BIPV system and interpret modules and inverter specification and choose an appropriate inverter configuration. In general, in this section, we will get an overview on the BIPV system and some specific problem about the BIPV system. And okay, now let's look at the typologies of a BIPV. As we usually know, there are several different kinds of the roof type. Sometimes it's a sloped roof, like the first one, and sometimes we're using a large size or large area flat roof, like the right-hand second one. And sometimes the BIPV system will utilize the facades, like the third one, using this area for PV power generation. And sometimes the BIPV system will be used as a shading device and use it as the to power generation. So there are also another four kind of BIPV system, such as a curved transparent roof. Sometimes the roof will be covered by the PV module for power generation, and the atrium for this one, the similar one, but for different function of the building. And we also sometimes with the PV system will install in the sloped rain screen cladding and the shading devices. The shading devices is like this one, but these two can have different shading ratio about the buildings. So, okay, we will talk about, after we briefly introduce the typologies of the BIPV, where we will discuss about the major building integration design issue. The first one is, the first one we need to discuss is about the useful area available for array. This one is very interesting, actually. So what is useful area available for array? Normally, we all know that the solar irradiation, the PV panel needs solar irradiation for power generation, but which is a high quality solar resources. So this is the first issue we need to consider about it is the solar access. What is a high quality or good solar access? And the second one is we need to consider the issue is the overshading and the partial shading. Perhaps most of the students do not know the shading effect on the PV panels. Actually, the shading effect has a very negative effect on the power generation, because if you have different shading on the same PV panel, the power output will limited by the lowest current or the voltage output, which will significantly reduce the overall power conversion efficiency of the PV modules. So this one, the shading effect should be considered significantly for most of the BIPV design. And the third one is the competition for the solar resources. This one is very interesting. So we all know that the solar resources normally is for day lighting. Yes, during the day we do not need to turn on the light for lighting, but the solar panel needs solar resources for power generation. So there exists a competition between the lighting energy and the PV power energy. So we need to take a trade-off between these two kind of sources. Okay, then the second section, we will need to talk about the generating performance of the BIPV system. The first one we need to talk about is the temperature and the ventilation effect. Actually, temperature and ventilation is correlated with each other, because the overall power generation, power conversion efficiency of the PV module is significant depends on the temperature changing. Normally, there exists an optimal temperature for PV module generation, normally at 25 Celsius degree. And if the temperature increasing, then the overall power output will reduce due to the intrinsic factors of the PV panel. So normally we need to keep the overall operation condition of the PV panel at around 25 Celsius degree and no higher than 50 Celsius degree. So this means that we need to keep the ventilation condition of the PV panel at a very good status. And for a good, if we got a very ideal ventilation, then the temperature of the PV panel will keep at a relatively high, reasonable range for its good performance. And the second one we need to talk about is the shading, as I said before in the section, bullet 1, and also the soiling. Soiling is For example, so what is soiling? Soiling is because there is a lot of dust in the area, and sometimes this dust will cover or partially cover the front surface of the PV panel. This will definitely affect the power conversion efficiency. We need to clean the PV panel regularly to remove this dust so that the PV panel can operate at a very good condition. But we also need to estimate the overall environmental conditions of the BIPV. For example, if you plan to construct a BIPV system for a building which is near a desert or a desert, or near the buildings with a very poor environmental condition, especially with a huge amount of dust, then the performance of the BIPV system will definitely very not good, because one is due to normally the soiling will become the first factors reducing the overall performance, because you need to spend a lot of time to remove the soiling covering on the PV panel, or otherwise the performance of the overall BIPV will be very poor. And also, besides the power generation, we also need to take about our concern about the performance as a building material, because a BIPV system also take a very important role as a part of the buildings to ensure the building have a very good water tightness and have the sufficient strength to support or to resist the external force from the nature of the building itself, such as wind, water, snow loading. So if we install a PV panel on the roof of the building, then this panel definitely need to support such strength. Okay, and the third one is thermal expansion. And actually, the BIPV system normally constructed by the PV module and its related parts. And this part is definitely different from the typically architecture materials. Sometimes maybe the thermal expansion may be another problem for the BIPV system, because the BIPV system definitely have different effect. For typical architectural materials, the thermal expansion is fine. Thermal expansion is fine to typically architecture, but for BIPV system components, it might become very important problem for the buildings. And the building codes is fine. Normally, we are not promoted around the world. And the standardized construction method and materials, easy of installation is an overall summarize of the above factors to ensure the BIPV system have a reliable and safety, both for the architecture building itself and have the ideal power output. In overall, there's three major building integration design issues, and each issues have a different small problem we need to concern. So we have overall overview on these major issues, so that we can ensure every step should be secure, and we can put forward our progress about building BIPV. And another one very interesting one is the placement of components. As we know, unlike the typically architectural materials, the PV panel or PV module will normally operate at around 20 years. After 20 years, this part of the overworking, overloading PV panel need to replace or install for a new set of them. So the replacement of a component is a very important issues in this BIPV system. So we need to ensure the three requirements as listed below. The first one is the accessible maintenance. What is the accessible maintenance? For example, we can maintenance the BIPV system at a very convenient method or low cost method. And we also need to use the varying lengths because the most of the BIPV have a power output. We need to, if we want to utilize or transfer this energy into the grid or used by the building itself, we need to wiring the BIPV system into the internal circuit or the external circuit for the grid. And the third one is the temperature of inverter and the modules. I believe most of the students know what is the inverter. The inverter is used to convert the DC power into the AC power because most PV module will generate the DC power, but most of our electrical load using AC load. So we need to use the inverter to convert the DC power into AC power for most of our electrical load. And also the temperature effect on the inverter has a very significant role. And normally there exists optimal optimal operation temperature for the inverter, normally at 30 Celsius degree. If we got this temperature higher than this degree, then the overall conversion efficiency will also decrease. There are definitely a conversion efficiency of the inverter, and not 100%. We will definitely cannot convert 100% of the DC power into the AC power. And the overall the conversion efficiency for the inverter is about 90% or even higher. This is not a problem. And the last one need to consider about the BIPV major issue is aesthetic and virtual integration effect. We need to definitely have a very idea is aesthetic and virtual integration for BIPV. We need to look at the whole BIPV system or have a very idea integration with the building. BIPV integrated, at least look at the integrated and could satisfy the basic load demand of the buildings. And okay, so let's move to the first category or the type of the roof system, the flat roof system. So what is a flat roof system? So the flat roofs have a sealed asphalt or membrane watertight layer, whereas slab roof can rely on overlapping tires or slides and gravity to prevent water from getting into the roof cavity. Definitely the water tightness is a very important property for any buildings, because if the water tight is not good, the whole building structure will be decreased by the penetrate water, and the whole building strength will be significantly reduced. So we need to ensure that we have a very idea the water tightness property of the building. And secondly is the array must be tailored for good solar access in most location. For example, normally for example in North Hemisphere air regions, we definitely cannot install our PV panel in the north face of the building, because most of the times the north face of the building have no solar access at all, which means we save time and energy to install this PV module because it did not generate any power at all due to there's no idea solar access. So before we start the BIPV system, we need to definitely choose the ideal solar access region or the area for such a solar panel installation area. And normally we're using the baluster and the rack mounted system are the most common for the flat roofs. And the next one is usually not integrated, since neither rack or baluster mounted system usually form part of the building envelope. This is very easy to understanding because the rack and the baluster mounted system is in general, we do not think they are part of the building, but form a part of the building envelope. So for these two kind of installation system method, it's not we cannot call it a BIP, but it's the most common installation method for the PV system as a roof PV system. And this next is large unobstructed areas may not be available on flat roof due to uneven load bearing capability, non-suitability for penetration and service equipment, which may cause shading. This part is very easy to understand. For example, normally most of the top roof of the building have limited load bearing capability. So once we design a BIPV or once we plan to install a PV system on the rooftop of the building, we need to definitely carefully estimate or calculate the bearing capability of the rooftop. Otherwise, we'll definitely distract the whole structure of the rooftop and will result in serious problems such as broken the water tightness property, or even broken the bearing capacity of the rooftop. So before we do the rooftop PV system installation, we definitely need to consider carefully about this problem. And the next one, the tilt and often the orientation can be optimal without affecting building forms, especially for the baluster and rack mounted system. In these two kind of system, we can choose a very optimal orientation based on the actual location or the actual environmental condition of the buildings. For example, normally we need the tilt angle of the PV system is strongly related on the associates of the geography. So it's normally with a fixed orientation, and we also need to remaining sufficient space between the PV module, because if we have not insufficient space between the PV modules, then some shading will be produced, and the shading problem will be discussed later. So we need to try our best to avoid the shading effect of the PV system. And the last one is the good ventilation of the PV. As I said before, the ventilation can keep the PV module at its optimal operation condition. And if we got good ventilation, the PV module can operate at its highest power output efficiency. And this one is a typically flat roof mounted system. We can see normally this PV module is installed on the rooftop, and they were installed as a very optimal tilt. And if we see that there's a shading behind the PV module, but this shading do not cover the PV module installed behind them, So in this situation, the shading problem can be ideally avoided, so that the PV system, this one, the flat roof mounted system, can perform a very high performance. Okay, and we will talk about the two kind of one is a rack and another one is a glass mounted system. So what is the rack mounted system? The rack mounted system are similar to those used for ground mounting of array. The rack is bolted to the roof, which usually requires penetration of the roof, and then may compromise between the watertight layer. Why is that? May compromise the watertight layer because the rack is bolted to the roof. If we use a bolted to the roof, then the roof structure or the roof water tightness property might be broken due to this installation. So we need to take care about the rack mounted BIPV system and the rooftop water tightness property. There is definitely we need to make a compromise or trade-off between these two properties. And the second one is the lateral wind load can be larger and the uplift force can also be experienced under certain wind conditions. Structure must be designed to standards. This means is if we're using the rack mounted system for BIPV system, then we need to definitely take care about, we need to calculate the wind load for the PV module, because if there is a great wind in the area, the PV module will experience the up force and the downshift for wind force at the same time. Depends on the wind direction. If we see this window, we can see if the wind blow from the front surface of the PV module, then the PV module will experience that force towards to the down area, and the modules are subjected to the downward force when the wind hits their front surface. When the wind strikes the back of the module, upward force is generated. Then the mounting system must account for force in both directions. So once we install such system, we need to carefully deal with the wind force, because if the system cannot hold the wind force, the system will be broken, and or even worse, the PV module will fly away from the rooftop and maybe hit some people or something, and cause some damage to the surrounding things. So we need to take about this one. And let's see some example of the rack mounted BIPV system. For this one is Sydenham, and most of this is a rack mounted system. So this is a sloped roof, and we install a rack mounted PV module on the sloped roof. So if we look closely, you can see the PV module are bolted on the roof. So this one is Sydenham, and another one is the Bruton Child Care Center, a very small system. Normally, it's a very small system, and this one is the Sydney Entertainment Center. Actually, there's no longer available over there, because why this example is most of in Australia, because I graduated from the University of New South Wales, and New South Wales is the most developed state of the Australia, and the capital city of the New South Wales is Sydney. So most of the real installed example is normally around Sydney, and I lived in Sydney for nearly 8 years. So most of this project are installed in Sydney, and this one is not in Sydney. This one is in Holland. Another great large project, rack-mounted BIPV system is the headquarter WWF headquarter of the ZIST. ZIST is the middle city in the Netherlands, Europe. If you see, this one is also rack-mounted PV modules, and this one is also another one, but not this one. We can see the rack-mounted PV module, but we also can see it is a facade PV module. So the WWF headquarters, including both and rack-mounted and the facade PV module at the same time. And after the rack-mounted PV module, we will talk about the ballast-mounted PV module. The first one is the ballast-mounted system. Normally use the gravity to hold the array down, so they no longer bolted to the rooftop, and do not need the roof penetration, but require heaviest ballast to hold the modules down against the wind load. This means we need to ensuring the top roof of the bearing capacity could hold such a ballast weight. Otherwise, definitely will cause some damage to the rooftop structure. And the last one is the roof and the watertight membrane must be capable of handling the roof and handling the load. So for the ballast and the racked system, we have very similar. We have for the racked and the ballast system, we definitely need to, for a specific project, we need to choose which one is the best one for the actual conditions. Every installation method has its advantage and drawbacks or the disadvantage. So we need to consider when we design or install a BIPV system. For example, if we have the bearing load capacity of the rooftop is very small, so we definitely cannot use in ballast mounted. But once we so we can only use the rack mounted system. But if we use this, we need to take care about its water tightness of the rooftop. Otherwise, it will cause a new damage to the system, to the system. Okay, and let's see, the next one is some real projects of the ballast rooftop, and this one is a flat roof, which is located in Munich, Germany, in BMW World Center. It's a kind of flat roof PV panel. You can see that. And all of the rooftop are installed by the BIPV system. And this one should be very familiar with this. This one, the headquarters of the BWM headquarters, located in Munich, Germany. And most of this system and you can see most of the rooftop are installed by the BIPV modules. Some are the racked mounted, or some are ballasted mounted PV system. Depends on the actual situation of the PV rooftop. And after we talk about the flat roof, we will talk about the inclined roof. The inclined roof products which mainly extend the roof panel shades or tiles. And water tightness, drainage, and the installation are important. But I think it is not due to it is inclined roof, so the drainage should be definitely important. Also, the drainage for the flat roof top is also very important. And the third one is can be used alongside the conventional products if appropriate modularity and weatherproofing details, and may have access to PV through roof cavity for maintenance and installation, and often free from shading because it is an inclined roof. So we do not need to select the optimal tilt orientation of the PV module, like in the case of the flat roof system. The inclined roof system has already inclined to ensure they have ideal water height and drainage. So we do not need to choose the orientation. We just need to install our PV panel or the PV tiles on the flat roof itself with the same direction with the roof. That's it, to ensuring the water tightness. And this one is a very extending typical sloped roof PV system. Is a standoff mounting, and we can see this black PV module bolted on the sloped roof, and to perform a part of the sloped roof to ensure its water tightness, and also provide power generation for the house by itself. I'm not sure whether it is connected to the grid or not, but if not, then this is if not, then we can call it a standoff or standalone PV system, BIPV system, which will definitely connect to our inverter and then convert the DC power into AC power to satisfy the household electrical power load. So the separate mounting structure may be no saving of materials, and the ventilation can be achieved. How can the ventilation be achieved is because we can keep a small space between the slope roof and its PV panel. There is a very few space between these two materials, and we can keep the ventilation at a very good condition. And Chrome Plaza, or most of the sloped roof, we can use this kind of the system. This one is 305 kilowatt photovoltaic system on Alice Springs Chrome Plaza. Alice Springs is a central city of the Australian. And from the overview, we can see the most of the plaza installed with a sloped roof were installed by PV panels, and the region is the size of the PV project is relatively great, it's large. And the second one is University of New South Wales Towering Energy Technology Building, which has the 150 kilowatts peak PV array. This one is a very. I was very familiar. I'm very familiar with this building because I worked in this building for nearly 6 years, and we normally do our experiments inside of the laboratory. And once we need to test the energy power conversion efficiency of the solar cell, we normally will go to the rooftop of this building to test the energy conversion efficiency of the solar cell in its natural condition rather than the laboratory. And one problem, what you may notice that most of the PV panel have different colors. Some are black and some are blue. Anyone know this is because if you see a PV panel in black color, then this kind of PV panel are made by monocrystal silicon, if you see the PV panel are in blue, in blue, then most of this PV module are fabricated by the multicrystalline silicon. There are two, both of them are fabricated by silicon, but the difference is monocrystalline silicon has a better performance, which means a higher cost, fabrication cost. But for the multicrystalline system, this means they have relatively low cost, but the performance is not as good as the monocrystalline system. So next time, if you see the PV panel are in different colors, you need to know they are fabricated by the different form of the crystalline silicon. And this one, the Tellring technology building is also a kind of slow through for BIPV system. In this stage, we can say that is an integrated building integrated system because the roof and the PV panel is integrated into the buildings. And if you see the rooftop like a wave, ocean wave, there is a space between the roof, the slides of the roofs. This one is used for the daylighting absorption. For normally in daytime, we do not need to turn on our lights if you work in this building because we have also sufficient daylighting. And another special or the feature of this building is all the electrical load can be powered by the rooftop BIPV system by itself, which means we do not need any other power from the grid anymore. So we can call this kind is a clean power building. And now for the sloped roof BIPV system, we're normally using PV tiles and shingles. For PV tiles and shingles, it has the provision for overlap is needed in these products for water tightness, and sometimes gravity secures tiles sometimes need to be tied down, especially if lighter than conventional tiles. And the tiled roof cavity may be ventilated passively via eaves and ridge actively by fan to cool PV or get a ideal ventilation condition and ideal operation temperature. And this may affect the thermal performance of the roof positively or negatively. Shingles are nailed or wired to a backing board on the roof structures, difficult to ventilate. And the last one is the roof tilt may often operate approximately optimal right-tailed angles. PV, the last one is the PV products that differ from countries to countries with varying local roofing methods. Yes, the area have different. For most of the students are from the Southeast countries, including Vietnam, Burma, and Thailand. So as I know, I used to travel to Thailand. I know the day lighting in Thailand is very good because it's very close to equator. And but the problem is if you're using a PV panel, you try to install a PV panel in Thailand, you need to carefully take about the humidity and operation temperature of the PV panel because normally I know the temperature is extremely high in Thailand, especially in summer. So we need to take care about this one. And we just show some traditional solar tiles. The traditional solar tiles is the solar PV or solar panel are integrated into the tiles, and the tiles can be used as a typically architectural tiles for slope proof and for also with good water tightness. And traditional roof tiles is like this one, and for the modern PV tiles, we have the PV tiles like this one. This one is also from the take a picture from the Netherlands. Most of the in this case, we can say that is a typically very good idea, very good building integrated PV system, because the PV tiles have a very good integrate with the tiles, and the tiles can be form a part of the houses. So this one is definitely a standard BIPV system. This one, the light blue with a mirror reflection is actually the PV tiles. And we can also see that one, this one, a new kind of the PV solar tiles, and for a slab-proof system. And this one is the installation picture of the how to install the slab-proof the PV panel. And if you see that normally, if you see the shading of this one, we can see the normally of this tile should be facing towards the sun. Definitely for it, if you are in the North Hemisphere country, then this face need to towards the south. If you in the South Hemisphere region countries, this tiles need to face the north. It all depends on the real conditions. So, and the tiles, the angle should be carefully calculated based on the geography location of the installation buildings. And here is actually this picture we call it the integrated roof panel, which means the whole slope roof are fully covered by the PV panels. Not unlike this one, because this one is partially covered by the PV tiles of the PV panels. So in this case, we can call this system is an integrated roof panels. The water tightness via panels with sealed watertight joints rubber and a watertight layer on the panels fixed to standing thin metal roof. And how to secure the PV roof have a very good weatherproof metal weatherproof. We're using several methods. The first one is weatherproof metal decking, and the second one we're using slatings, and the third one using the weathertight seals. All of this can secure the weatherproof. And the integrated roof panel is this one, also a slope proof. It's also a slope proof top. So so here we come to the next problem or the issues is about the watertight sheet on the PV. How to secure the watertight performance, or how to secure a good watertightness of the roof for a BIPV system. And we definitely need to use a watertight sheet on the PV system. For normally we need to ensure the air gap of a good ventilation. So air gap for ventilation and the watertight should be all taken into consideration into a BIPV system, especially for the slope-proof system. The PV well integrated into the building design have this one is an example. The PV well integrated in the building design is a 5 million watt site like Jetty Holland. Now well integrated as a slope-proof BIPV system, and the PV system forms a logical part of the buildings. It's played a very important part of building as a roof. And this roof should have a very good ventilation for the BIPV power system, power output, and also it will need to have a very good weatherproof to prevent the water penetration during the raining day or the snowing day. The rooftop should also have the very good bearing load capacity to hold the snowing on the top of the roof. And this one is a huge a lot of the houses with a very similar roof. And also we can talk about flexible substrate PV module. And the flexible substrate PV module have 3 features. The first one is design flexibility, because the substrate is relatively flexible. And the second one, as we said before, is should have a very good lightweight to reduce the requirements or the requirement of bearing load capacity of the rooftop. And the last one is also the weatherproofing, including the water tightness and something like that. So here we introduce another one, unlike the silicon-based photovoltaic solar cells, we're using amorphous PV on flexible metal substrate. And normally the flexible PV module solar cells, we're using the CIGS and the CDTE, but unfortunately, both of these solar cells have toxic materials. CIGS is short for the copper integrating gallium and sulfur, and the CDT is another amorphous PV solar cells with a flexible substrate. So the substrate is flexible, and which means it's a thin because they are thin, so they have relatively low weight. So they can easily cover on the rooftop of the system, but the performance, the performance of this solar cell is very poor, relatively poor, much poorer than the silicon-based solar cells. And they have another very important problem is the optical decay problem, which means most of these amorphous PV panel have very limited operation work time. After that, the overall power conversion efficiency will be reduced significantly. For example, if you at first later such amorphous, for example, CIGS amorphous PV panel have a power conversion efficiency around 10%. The 10% is actually much lower than the conventional power conversion efficiency of the silicon-based solar cell, which is typically 20 to 25%. So the amorphous PV solar cell is only half of the silicon-based power conversion efficiency. And after they operate for example, for a few months, the power conversion will decrease to maybe a half, which is 50%, 5% of the power conversion efficiency. But these are the low power conversion efficiency and the optical decay problem is the 2 major disadvantages for such amorphous PV solar cells. But such kind of amorphous PV solar cells have this advantage. For example, the first one is because they are flexible and thin, so the all fabrication cost of amorphous PV solar cells is relatively cheaper, much cheaper than the silicon-based solar cells. And the second one is amorphous PV solar cell have very good working performance at weak light resources. For example, for most of the north face, in North Hemisphere countries, we all know that in our north face of the wall of the roof, there's very limited light. But the amorphous PV can be used in this area because they have very good weak light performance. So if you if you're using the amorphous PV module installed on the north face of the wall and the north roof, then definitely we can have a better performance if we're using the silicon-based solar cells. And this one is we be using a printed technology to prove the flexible amorphous solar cells. Unisolar roof. This one is typically using the amorphous silicon solar cells. So they normally can form a very huge area without any wiring or something like that. So sometimes use this one, and I believe most of our calculator using the amorphous PV system for temporary power generation. Here's another project using the amorphous silicon solar cell on sheet metal roofing in Kogra. So this one is another very big plaza of Australia, and the whole roof is covered in PVE. This PVE is amorphous silicon solar cells. So as I said before, the amorphous is cheaper but less efficient than the silicon-based solar cell, and amorphous performs differently compared to the typically silicon-based solar cell. For example, the less loss and less energy loss at high temperature and weak light condition. Because it is flexible and have different performance, so the chimney ventilation fans and so on are solar obstructions, but does not matter too much, because even though in weak light conditions, amorphous silicon solar cell can perform even better than the conventional commercial silicon-based solar cells. And the last one is after the roof. After we talk about the flat roof or slab roof, we'll talk about the arterial and the skylights for the BIPV system. The arterial are constructed by securing and sealing transparent glazing units onto a metal frame. The atrium are considered to be a part of the roof structure, and while the skylights penetrate a conventional roof to provide light and sometimes ventilation, and also can either be a single frame glazing unit or a long span of the glazing, such as in a warehouse, shopping center, and so on else. The last one is a photovoltaic module can directly replace glazing in skylight or atrial. The final point we need to consider about is cabling can be run through the framing. So basically, the atrium and skylight have a very similar function, but they have also different, very similar function, but slightly different. Yes. So, as I said before, for a BIPV system, we're using the daylight for power generation. In the view of energy conversion, we will convert the light energy into the electrical energy directly, but we also, especially in the daytime, we need the daylighting for interior lighting. So there is a trade-off of how to dealing with this conflict between the PV power and the daylighting. We're using the solution is presented in this real project in the Dogen Town Hall. If you see that this skylight of the skylight of the town hall, and a part of the skylight are covered by the PV panel, and another one is transparent for daylighting. So in this case, we can got sufficient power generation through the BIPV system, and also we got sufficient daylighting. So this one is a very ideal solution for the conflicts or the penetration between the two resources. So if we look closely to this PV panels, we will see that there are several hole-punched monocrystalline silicon. The hole-punched monocrystalline silicon, the hole is also used for daylighting. We cannot fully cover the roof. Otherwise, if in this area there's no uncovered glazing. So if we want some sufficient daylighting, then we definitely need to produce some hole in the monocrystal cells. So this one is another solution for BIPV system. Skylight. This one is a overall side view of the PV skylight view. Here you can see the daylighting, and they are designed for the daylighting and the tilt area possibility for better performance of the PV modules. And if we see that this one is using for daylighting, and part of the optical energy is using for daylighting, and the remaining one is you might okay, and after the rooftop have a different roof incline angle, but this incline angle affecting the solar energy generating capacity. If so, what should be the recommended angle of this solar panel? Dynamo is a dynamo. So yes, I can explain. I can explain what is the optimal. What is optimal? What is well, I know how to know the answer, but I need to check the word. So hang on. Okay, so the Simon Sonam is the Sonam. Sorry, I don't know how to pronounce this. So Sonam, yes. And you asked one question is what should be the recommended inclination angle of this solar panel? The recommended or the optimal inclination, we call it inclination, normally tilt, T-I-L-T, tilted, T-I-L-T-E-D. Tilted angle is we using the tilted angle around the latitude of the region, latitude. Latitude, the recommended inclination always said is tilted angle should be latitude angle, local latitude angle. I think I can answer this question. It depends on the location of the latitude of the BIPV system. If we got the latitude around the 30, then the recommended inclination should be 30 plus or minus 2, which is 28 to 32 degree. it should be the optimal tilt angle. Do I need answer your question? Okay. 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 Because I want to I forgot how to spell this one, so I just check the dictionary to how to spell this one. Yes. Okay. Okay, then we move to the next part is we just look at the PV skylights. We also know that the PV sawtooth roof. The PV sawtooth roof is in this one is a glazing penetration. So there exists a tilt angle, and this angle is latitude. It depends on the optimal tilt angle, and they can be used for PV system, and also from the back surface. The front surface is used for power generation, where maybe the PV module with some punched holes, and the back surface is uncovered any PV module, so it's just for the daylighting. So if we stand under the sawtooth roof, we should have sufficient daylighting, and also we can get sufficient power generation through the PV sawtooth roof PV system. Like this one. This one is actually the interior view of the sawtooth PV system, PV roof. If you see that this side normally is not front sun, and this side is just a glazing on the glasses for daylighting. And the front surface, we see huge about the PV module with a hole punched on the side, or sometimes we will adjust the array allocation of the PV solar cells so that there exists some punched holes to allow the lighting penetration through the hole for daylighting. So a back surface and front surface for daylighting, and the front surface for PV power generation consists of the sawtooth roof power system. And another one is very similar to the skylights and the sawtooth roof system is the PV atrium. PV atrium. The PV atrium is also very similar to this one, but you see there's a in front of the surface will be installed by the PV panel, and the back surface is covered by the glazing, uncovered by the in this surface will not be covered by any PV panel. So this one we also say that this one is for sufficient daylighting collection and the power generation. This one is the inside of the atrium. The large area, the skylighting. And the last one is the curved roof wall. This one is University of Melbourne, and we're using a curved wall. Yes, it can call it be wall. Wall is a kind of covered by the, I think it's a multi-crystal silicon-based PV panel, and which a little curved wall for power generation. And also we need to take care about, especially for this, the light reflection of the PV panel may be caused light pollution. Yes. And if we look inside of this kind of curved roof PV system, we can see that from the inside we can get sufficient daylighting, and also we can get sufficient power generation through the installed PV system on the rooftop on the roof, on the wall. And this one is another typical applied project of the curved wall, the BIPV system. And also normally, if you can see that normally it will be supported by another side for the daylighting. And this one is fully covered. So in this side, we can also collect any daylighting from the surface, but the daylighting can be collected on another surface. So in general, the PV walls and the facades, the walls provide weather protection, and the appearance is a high impact. We need to get very aesthetic performance of the walls. And in facade, the material replaced by PV is also often expensive, or which will reduce the net system cost. Yeah, something like the material. If we replace the wall material from concrete into the PV system, the semiconductor material is much expensive than the traditional concrete material. So if we try to install a facade the PV system, the overall net system cost will definitely increase. And another one is the BIPV walls will usually not be optimal tilted, especially not close to equator. For example, in Australia, but for our country, for Southeast countries, most of the country are very close to the equator, so this should be not a big problem. Sometimes I believe most of sometimes the sun will appear in north. It depends. Sometimes the sun will appear in the south, and sometimes the sun will appear in north if you are close to the equator. So which means the sun, yes. So we will discuss. If we want to install a BIPV system, we definitely need to take care about which is the optimal tilted angle. I believe the slope-proof BIPV system should be the most appropriate solution for the Southeast country if you want to for the Southeast country, because most of the country are very close to the equator. And in New South Wales, the state of New South Wales, the PV altitude for vertical was typically 1/3 or less up to the roof. And this means we do not recommend it to install the PV walls or facade. If we have sufficient area on the rooftop, we encourage you to install the BIPV system in the roof rather than the wall, because the overall power output is much higher than the wall PV walls. And also, if the PV walls will cause another problem, such as construction bearing loading capacity, something like that. And for after we said that the optimal tilt orientation can be achieved by using sloped or sawtooth design. Yes, because for wall we have no choice to decide the wall can be tilted at a specific angle, but for the rooftop we have sufficient options to choose how to design our optimal tilt angle, something like that. So the optimal tilt angle is closely related to the latitude of the BIPV system location. And the more shadings of facades and roof due to obstruction close to the horizon. As I said before, we need to try our best to avoid the shading effect. The rooftop system apparently has a better location and condition compared to the PV walls. So this is another reason to encourage us to install the BIPV system on the rooftop rather than the wall. And additional thermal expansion due to PV needs consideration. And the last one is additional weight of PV. Both of this one is more in terms of the structure of the buildings rather than the power output. So let's see the thermal expansion. The PV panel will thermal expansion more extremely due to heat production of PV, because PV module is a kind of operation devices. For an operation devices, it will definitely generate more heat or thermal than traditional construction material like concrete. And so we need to provision must be made for expansion. Provision must be made for expansion, and otherwise the PV model will squeeze with each other and broken the whole structure of the PV model itself by itself. This is another problem. So another one is the curtain wall is exterior wall supported wholly by metal or concrete structure frame of buildings. The curtain walls is another option for the PV walls. So in PV walls, we're using the PV wall themselves as a supported structure for the building, but it have a lot of intrinsic problems like the thermal expansion, and maybe the solar panel themselves do not have sufficient strength to hold the whole buildings. So this requires we need to carefully design when we're using PV model. But a curtain was a very good provider alternative way to, if we want to install PV walls, because curtain wall do not need to consider anymore about the architecture or building structure, because the PV panel no longer play the role of building bearing loading capacity, because they are installed is supported by the metal or concrete structure frame of a building, and carries no loads other than its own weight and wind load structure frame transfer load to ground. And this one is also similar to what I said in the first point. And the third point is panels may be vision glass, opaque spandrel units, thin veneer panel of concrete, stone, masonry, metal. And so we need to consider the following factors. The first one is the pressure plate. Is a panel mechanically held by framing and can cause shadowing on module. And the second one is the structure silicon glazing and panel glued to the frame and can cause the issue with the weather seals of module edges and no overshading issues. The last one is the pre-assembled frame panel may be harmed from a frame. So the following these points I need to consider when we try to using a curtain wall instead of the PV wall. So the PV curtain wall can be used for cabling, and then need for place to put the cabling impact frameless and appearance. The facade has more irradiation further from equator, and the double glazing PV panel are commonly used. This is because the outer pan laminate glass, PV glass, the inner pan glass with a sealed air gap, but one for laminate, and the outer pan laminate for laminate, and the inner pan for sealed to prevent the thermal expansion or the provide an idea of good ventilation condition, and may not provide equator ventilation for PV. And the last one is the heat dissipation more difficult than for rooftop system. the wall system is usually sealed because the wall is usually sealed, so the heat dissipation becomes more difficult than the rooftop system. This one is especially curtain wall, combination of transparent and semi-transparent and clear glazing. These are typical curtain walls. And for more details, the example of the curtain wall details, we can see there's a double glass panel with the PV solar cells. The outer side and the inner side of the panel have the glazing, one for lamination, and another, the inner one is for the sealed. This one is typically the panel, the curtain wall details like this one. The blue side is should be the curtain walls, and the transparent glazing is for daylighting. The plate seems like a window or something like that. Definitely, the curtain wall is very expensive compared to the traditional PV module, because they should have double glazing, and they have mechanical parts, and they have a specific structure bearing loads. So they definitely is expensive than the commercial PV silicon-based PV modules. That for a real case is CIS solar tower Manchester in United Kingdom. If you see that this one is all made by the PV curtain wall, and this wall is seems a blue one, which means most of the PV module is made by the multicrystalline silicon-based PV silicon PV modules. There is another kind of one, the curtain wall is a sawtooth curtain wall. It's very similar to the sawtooth rooftop, very similar one. And this one is used to provide shading devices. Because sometimes we do not need too much, especially we do not in China, we do not need to in the afternoon, the sun is in the west, but as this time the sunlight in the west is not so friendly. I think they're not healthy to the people working. So we definitely need some shading devices. So the sawtooth curtain wall plays a role of the shading devices. So partial of the we can accept the morning solar irradiation, and we can in the morning we can get access in the morning we can get access to the sufficient daylighting, and in the afternoon the daylighting is too strong, so we can using the sawtooth, another one in transparent wall to prevent the daylighting. And so we got the three features of the sawtooth curtains. So first one is the optimal orientation. We can design by ourselves to choose an optimal orientation and a minimum additional construction cost, and the multiple corner windows, which means the corner window means shading devices. This one is another curtain wall, and we can see that there is in different direction compared to the sawtooth. This one is called accordion curtain wall, and if you can see that the sunlight will incident on this side, and this side is normally can be using as a shading, and which means we do not need too much sunlight, and the sunlight can come from the lower side, lower another angle, which is installed through the transparent glazing, and on the upper side is normally in the PV panel for power generation. This one is a very typical PV mounting the accordion walls. And Also, the ring screen cladding is another one for the BIPV system. The secondary, the ring screen, according to the ring screen is a secondary weather protection, not watertight, prevents the facade from becoming saturated. Cladding panels are set off from the building structure to allow for drainage and ventilation on such as cladding rails. The outer layer is not sealed. The inner layer is weather tight and can be retrofitted to existing buildings. And there is an air gap allows the ventilation for modules and space for cabling. This one, the ring screen is very similar to the PV board and the curtains, and just the function is different. This one is a ring screen cladding details, and we can see very similar cladding rails. The ventilation and the cabling zoo is installed between the cladding rails, and the cladding rails is installed on the building structure, and the building structure in the insulation. This one is a flat Holland's Rotterdam in Rotterdam is in a famous city of the Netherlands. This one is a sloping wall. It's a sloping wall. It can optimal tilt possibility and but inefficient use of building footprint. So in this stage, we almost we went through the different kind of the BIPV system in the top rooftop system and in the wall PV wall curtain system, and similarly in generally there is we definitely recommended to install our BIPV system in the rooftop rather than the walls, because they can provide more power generation and low cost. And more importantly, we do not need to in the rooftop BIPV system. We only consider about how to generate more power rather than the structure bearing load capacity and something like that. So in general, we strongly encourage to install apply the BIPV system in the rooftop. And sometimes the rooftop and another one, the rooftop is another advantage is it can adjust the tilt angle. But if the PV wall cannot use to adjust the angle of the walls. Okay, so we move to the next part is light filtration and shading devices. So what is the PV photovoltaics is used to enhance or reduce light and heat entering a building. Opaque or semi-transparent panel are warnings because they have a good opportunity for optimal tilt and maybe fixed or tracking and have a good ventilation. Glazing for windows or skylighting, sometimes they have the following features. The first one is the semi-transparent thin film PV products. And the second one is the opaque PV patterns in clear encapsulation, interesting daylighting effects. Cost of the PV offside against the conventional shadings, and simple construction structures are often already designed to support the shading structures. So we give several examples of the PV shading devices. First one is they have the following features. For PV shading devices, the first one is weatherproof. It definitely need to have a good weatherproof sealed of building and not compromised. And wiring must penetrate the building. And the last one is a new easy new retrofit construction. So in this case, PV panel can be applied as the shading devices for power generation. These are some real picture of the BIPV for BIPV shading of PV for shading devices. And another one is very interesting. The above system we are talking about the fixed BIPV system. If especially we can also using the tracking shading devices. This one is in Switzerland. So the tracking system have rules of a very. The tracking system means the PV panel can tilt or can change its direction and tracking the sun track, and which means the performance of the PV panel can get relatively good along the whole days to get the maximum sunlight for power generation. But this will important in some important places. If you need to sufficient and some important buildings, if you need to ensure the power generation, sufficient power generation, then I recommend you to using the tracking shading device tracking system, not only for the shading device, but for the tracking, but the overall cost will be increased significantly, which means most of the area we should using the fixed system, something like that. Okay, this one that is and we will talk about what is a BIPV shading, what is the disadvantage. So, for example, partial shading in summer be very designed from Europe. Shading devices for shading we need to try to avoid the shading effect on the PV module, which means if we can using the BIPV system as the shading devices to avoid but the shading caused by the PV panel cannot be affected on the other PV panel. Otherwise, the overall performance of the PV system, BIPV system, will be significantly reduced. That's the first chapter of the BIPV system, and if you have any question, you can just type any problems in like Sonam in the chat window, and if I see that, I can answer your question in time. So in next part, we will talk about some technical issue in the BIPV system. Maximum power points here, according to the data, we can got a maximum power point here. Here is from this line we can find the maximum power point, and from the IV curve we can confirm that same voltage, we have a corresponding current. We say this one is a maximum power point. So here in this figure, this figure, we can say we call the interceptor of the vertical axis. Vertical axis is called the short circuit current. And for another one, the interceptor of the horizontal axis, we call this voltage is open circuit voltage. So how to estimate the overall performance of the solar cell? We said that actually the power conversion efficiency is output power divide the ratio between the output power and the input solar irradiation. The ratio between them is we call the power conversion efficiency. And the power conversion, the output power conversion can be achieved by the P equals to P stand for the PV output and G in stand for the incident solar irradiation, both are in the unit of volt. So the total power output can be using the V maximum times I maximum, something like that. And so we need to know that the current is the generated current by the PV solar cell is proportional to the area of the cells, and the voltage is independent of the area. So we need to take care of it. And also the current is proportional to the light irradiation or the incident. So the current density is also proportional to the light density of the incident light. So, and the VOC, we just said the ISC, and how about the VOC? VOC is a characteristic of the solar cells materials. It's only related to the characteristic of the solar cells materials, which means for typically maybe some knowledge you are not very familiar with is VOC for silicon-based VOC. It is around 0.6 volts, something like that. It is strongly determined by the band gap of the silicon material. If we are using if the solar panel is fabricated by another semiconductor material such as gallium arsenide and germanium, then the VOC is definitely different. It's all depends on the semiconductor band gaps of the material. So in other words, the VOC is the characteristic of the solar cells materials. And okay, so next one is the IV curve modules and arrays. And